Hi, Assalamualaikum and very good afternoon. Today we will present about thermodynamics in Otto cycle and another application which is heat pump. So this is our group members which is include Natasha Azira, Ahmad Shah, which is me, Sute, Nurul Wajiha and Muhammad Shamil. So for our introduction, we will discuss about what is heat pump and also what is Otto cycle. So the first point, what is heat pump? Heat pump is a device that transfers thermal energy from one space to another space, typically between an enclosed space to the disclosed, to the outdoor. When they use a heat structure, energy is transferred from the outside into the structure. By transferring heat from the building from the outside, heat pump can also function as air conditioner. The refrigeration cycle is used in the process. The refrigerant at room temperature is compressed in heating mode. As a result, a refrigerant is heated. This thermal energy can be used to power the central heating system. The refrigerant is decompressed after being moved back outside. So next, Otto cycle is simplified a thermodynamic cycle that describes how typical spark ignition piston works. It is the most common thermodynamic cycle found in the automobile engines. The Otto cycle describes what happens to a mass gas when pressure, temperature, volume, and heat addition and heat removal are changed. The system is the mass of gas that is subjected to the change. The fluid gas within the cylinder is defined as a system in the sketch. By describing the change that occur in the system, it will also describe the system effect on the environment in reverse. The system of the Otto cycle will be generate enough network for the system to propel an automobile and its occupant to environment. So our objective are to understand and to apply understand about lecturer syllabus, which is heat and work, the first law of thermodynamics, and numerous other factors. It is critical that we can put what we have learned in university to use. The following goal is to be able to explain about heat pump and Otto cycle. Furthermore, we can demonstrate the calculation involving the heat pump and the Otto cycle. Next, I will pass it to my colleague to explain about heat pump.
Hi, Assalamualaikum and a very good day everyone. My name is Natasha Azira. I will present about the heat pump. Heat pump removes heat from a low temperature body and deliver heat to a high temperature body. To accomplish this energy transfer, the heat pump receives external energy in the form of work or heat from the surrounding. The components of a heat pump include a condenser, expansion valve, evaporator, and a compressor. Have you ever wondered how a heater produces warm air? For the first step, the pump transfers heat that occurs from the working fluid in the evaporator and uses the cold air outside to turn it into a gas. Then, the compressor is able to increase the temperature and pressure of the gas. Then, the hot gas is forced through condenser coil inside the heated area, where it condenses back into a liquid and distributes heat to the area since it is hotter than the area being heated. Finally, a valve that lowers pressure causes the liquid to flow back through it, cooling it and allowing the cycle to continue. So as you can see, these are the formulas that we use in the heat pump. So for the first one is the coefficient of performance for a heat pump equals to QH over work net in, or QH over QH minus QL. And the next one is the heat pump efficiency is expressed as coefficient of performance beta equals to heating sort over energy needed.
Okay, so for the calculation of a single unit, a steam power plant produces 50 megawatt of net work while burning fuel to produce 150 megawatt of heat energy at a high temperature. So, to determine the cycle thermal efficiency and the heat rejected by the cycle to the surrounding, we must use the formula given to us through the application. So, firstly, for the thermal efficiency, we must use the formula of efficiency, which is the work net out over QH. So 50 megavolt over 150 megavolt is equals to 0.33 or 33%. So the efficiency of this steam power plant is 33%. Then, to find the heat rejected by the cycle, we must use the formula of work net out equals to QH minus QL. And the QL is the heat rejected. So QL equals to QH minus work net out, which is 150 megavolt minus 50 megavolt. And we get the final answer of the heat rejected equals to 100 megavolt.
Hi everyone, welcome to introduction of Otto cycle. The Otto cycle describes how heat engines turn gasoline into motion. Like other thermodynamic cycles, the cycle turns chemical energy into thermal energy and then into motion. So now I will explain about 4-stroke engine. The stroke refers to the full travel of the piston along with the cylinder in either direction. When intake valve is open, and this is what we call the intake stroke, piston travel downward from top dead center to bottom dead center to draw the air and gasoline mixture into the cylinder. So as you can see, the volume increase. Next is the second stroke. Pistons travel outward to compress the air and gasoline to make it a combustible mixture. So since this is the compression, and as you can see, it's clearly the volume decrease and the pressure increases. This is called the compression stroke. Before moving to third stroke, we will need something to give us power, and that is where combustion comes in. Here the spark plug now ignites, provide heat to the fuel oxygen, which will produce combustion. The combustion is what we call the heat addition to our engine, and of course the pressure increase. Now we can move to the third stroke by utilizing that heat energy from the combustion. So here the pressure now decrease and the volume increase, and this stroke is what we call the power stroke. It's called the power stroke as this is the power that move your car and will keep the cycle from going around. Now after using the air and fuel mixture, heat waste will now need to be evacuated. This is what we call the heat rejection of our engine. The exhaust valve is open to assist evacuation of the waste gases from the cylinder, making the pressure to decrease. And finally, the last stroke will now be used as we need something to evacuate the waste out. The piston will now travel upward to push out the waste gases, and this is what we call the exhaust stroke.
In general, the thermal efficiency (NTH) of any heat engine is defined as the ratio of the work to the heat input at the high temperature. Since energy is conserved according to the first law of thermodynamics and energy cannot be converted to work completely, the heat input must equal to work done plus the heat that must be dissipated as waste heat into the environment. Therefore, we can rewrite the formula for thermal efficiency as NTH equal to W over QH equal to QH minus QC over QH equal to 1 minus QC over QH. Since during an isochoric process, there is which is the formula is V2 over V1 to the power of K equal to T1 over T2 to the power of K over K minus 1. It also can be derived that T4 minus T1 over T3 minus T2 equal to V2 over V1 to the power k minus 1. Lastly, when we rewrite the expression for thermal efficiency using the compression ratio, we conclude the air standard Otto cycle thermal efficiency is a function of compression ratio and K equal to Cp over Cv. And lastly, the equation we got is NTH equal to W over QH equal to QH minus QC over to QH equal to 1 minus QC over QH.
So, in conclusion, the fundamentals of heat pumps were presented together with the working principle of the thermoelectric heat pump, the absorption heat pump, and gas compression heat pump, and the vapor compression heat pump. It should be noted that vapor compression heat pump driven by electricity dominated by the current market. Heat pumps are very energy efficient and therefore environmentally benign compared with the other available heating technologies. The technical and economic performance of the heat pump is closely related to the characteristic of the heat source. The cycle are ideal cycles for every type of combustion engines. As the cycle is an ideal cycle for petrol and gas engines, similarly, there will be another ideal cycle for the diesel engines too. Even though the Otto cycle is ideal, it cannot achieve the maximum efficiency, but we can improve the increase the efficiency of the cycle with a few methods.